So welcome to HTTP2, and my name's Rob Crowley. So for a day job, I work at Bank West, where I'm the technical lead for APIs and their authentication platform. So on a day-to-day basis, I spend the vast majority of my time around the back-end server side of things, and part of that is performance is really key to my role. And that's really going to be one of the viewpoints or lenses through which we're going to look at HTTP2 today. So we've got quite a number of things I want to cover. So first of all, I want to give you context. I want you to understand why HTTP2 is a thing. How did it come to be? What was the rationale behind it? We're then going to look at the major features. What's changed with HTTP2? What do you need to be aware of? We're then going to dig into one particular feature, server push, which I think is probably the most misunderstood feature or part of HTTP2. And we're going to look at the current browser support for that. So there's a few rough edges right now. I hope for today I will give you the information that you will need to be successful using it or applying it to your own servers. But most of all, I really want everyone in the room today to get a solid understanding of the category of problems that HTTP2 will help you with, and for you to go back and continue to learn it yourself. Realistically, we only have an hour today, so I will not be able to make you experts in it in 1 hour. But if I can instill in you that passion to learn that little bit more, that would be success for me. So HTTP2 is really, the next incarnation of what is the workhorse of the internet. There are millions upon millions of devices that use HTTP every day to transfer data across the web. But HTTP is not an island unto itself. It actually forms part of a stack. And there's actually a number of different protocols in place to actually get your requests safely to the server and back again. So we're going to spend a little bit of time digging into the role that each one of these protocols has to play, because this will give you a better understanding of some of the pain points that we have with existing version of HTTP 1.x and what we tweaked and improved in HTTP2. So when we're talking about HTTP, we're really talking about the left-hand side of this. So we've got like the application level protocols up the top. Then we've got TCP at the transport layer, IP, so IPv4, IPv6 at the internet layer. And finally, we have network access down the access layer. But what do each one of these layers do for us? So when we're doing anything about explaining network layers, it's always good to look at the Osi model. There's a standard for defining, what responsibility should sit with, each layer. So starting with the network access layer, here we're really talking about physical bits going across a network. So at layer 1, we're talking about physical medium. How do we send a physical bit across that wire? Layer 2, we go up a level of abstraction. We're now talking about reliable delivery between two nodes on a physically connected network. Where the IP protocol or the internet protocol comes into play is at layer 3. Here we're talking about addressing. So again, the internet is huge. It's not all in one physical network. You need to have addressing and routing. And that's where the internet protocol comes into play. Then you have transport. So in this case, TCP. This is all about reliable delivery of data. So retransmissions if it fails. In-order delivery. So this is really where your quality of delivery comes in. This is everything that says, okay, how will that data actually get from the client to the server in the same order without something going missing or going awry along the way? Session then is about continuous communication between the client and the server. So the web today isn't about a single request and a single response, but we load web applications that have numerous interactions between the clients and the servers. And this is where we maintain that connection. And then finally at layer 6 and 7, this is the sort of level of abstraction that we mostly deal with. So when we're writing web apps, we deal with data that's already decoded, that we're dealing with resources, not datas or frames. It's actually at that resource or application level. And there's one other bit of introductory information that I think we should all be aware of, because this has a huge influence on web performance today. And those two things are bandwidth and latency. So if the 8 fallacies of distributed computing have taught us anything, it's that bandwidth is not infinite, and the network is definitely not heterogeneous. You can see from here that from the client to the server, you may actually pass through any number of networks. And some of those networks might have very high bandwidth, insofar as you might be able to fit a lot of data across that pipe at one point in time. Or in this case, we can see cable, there's less data. The volume of data you will be able to send end-to-end is going to be constrained by that bottleneck. And that's a key thing. That is your effective bandwidth. There's another facet as well, which is about latency. And that is the speed of light. And that's about 300,000 kilometers per second, which might sound incredibly quick, but in networking, it is actually appreciable. And in fact, it's actually the far harder problem to solve. With bandwidth, we can just put in more cables. We could just put in more, optic fiber here, or cabling over there, and just increase that bandwidth. We can get out of that trouble with money. We haven't found a way to solve the speed of light as yet. So what we're going to do for the next few minutes is take a whistle-stop tour around the history of HTTP, where it started and where it took us to today. So it all started with Tim Berners-Lee back in 1990, and it's HTTP 0.9, and really this was the ultimate minimum viable product. Like, he really got how to do simple. I don't think you could actually have it any more simple than this. You could open a connection, you could issue a single GET request to a particular resource, you would get some hypertext document back, and the connection would be closed. That's it. But for the use case that he had in mind, which is basically passing scientific documents between scientists at CERN, it was perfect. But of course, other people wanted to do other things with it as well. So between the periods of 1990 and 1996, there was a huge amount of change, and really ad hoc change. So we weren't happy with text alone. We wanted to introduce images and rich hypermedia. We wanted to say, okay, well, actually, sending these images back and forth across the wire every time, that's not too smart. We wanted to introduce caching. And really, with HTTP 1.0, it was really a reaction to what was happening. So, wow, so much stuff is happening in this space, let's just write it down. So it wasn't a formal specification that you could actually code against. It was really just an attempt to catalog what had happened in that space. Fast forward to 1999 and HTTP 1.1. This was the first formal standard that actually came to be. So this is the first time that if you actually took that implementation and coded against it, there was a fair chance that a client would actually be able to operate against it. And it was an absolutely massive success. So in fact, HTTP 1.1 is the web that we all know. It's what we would have been building against our entire careers. And it's really been the cornerstone of the web for almost 2 decades. And it's an absolutely amazing feat. And it gave us a couple of really interestingly powerful features. So you would have remembered back with HTTP 0.9 and 1.0, it was a single request response. We would have opened a connection, made a request, pulled down the response, and then closed the connection. In 1.1, we got keep alive. So now for the first time, we could actually make multiple requests on the same connection. Really good for performance. They also looked to introduce a feature to improve parallelism across the protocol. It's pipelining. Probably some of you might not have heard of that, and that's because it never really took on. There was a lot of implementation complexity around this. So effectively what we were looking at with HTTP 1.1 is effectively still having a serialized process. One request, one response. So what we're going to do now is travel back in time and take a quick look at, well, what websites looked like in 1999. This is Yahoo. So this was one of the most popular sites on the web at that point in time. So actually some of the content's still, pretty relevant. But if you think the page looks impressive, check out the markup. Like in one case, we actually have tables that are 4 levels deep. There was absolutely zero semantic markup here. And yeah, I was around this time, it was awesome. Tables, you could absolutely get a job as a web developer, You knew call span, you were ready for promotion. So Google, possibly the company that you would say that is the biggest web giant today, they're still in beta. They haven't even gone, live yet with, a full production product. And if you're wondering what the layout is here, it's a table. So you've got an idea now of what HTTP, the protocol, looked like, what sort of sites we were building, at that point in time. So what got us thinking about a new version of HTTP being, required? So obviously everything's looking good, then this happened. Well, okay, even with the massive amount of tables and clip bars on my side, I didn't quite manage to break the web. What started to really sort of like tip the balance, though, is sort of what's been coined Web 2.0. And this is really just a phrase that Tim O'Reilly popularized. But it's to mark the sort of change between consumers just pulling down data from the web to actually contributing it back, so user-created content. And this really changed the sort of like landscape of the web. So we went from just having plain documents to web applications. So we were looking for richer experiences. And in fact, between 2004 and 2009, the average web page size tripled. That is partly due to content and partly because people weren't happy with the limitations of HTML in terms of like crafting experiences. So we introduced JavaScript and a whole bunch of other things again to, make the experience more interactive. And to put that in context, there's a site called HTTP Archive that basically records interesting stats about sites, over time. And unfortunately, its data only starts back in 2010. But what we could see here is back in 2010, the average website had about 80 connections to pull down the entire, 80 resources to pull down the entire site, and about 700 kilobytes of data. You can see that this is a massive spike. So this is accurate as of yesterday. We now have the average site requiring 108 connections to the server to pull down the data. But even more so, over 3 megs worth of data. Like, that's absolutely bonkers. I don't think Tim Berners-Lee could even have imagined that when he originally created it. But there's a more subtle problem here, is that TCP is actually optimized for long data flows. Like, it is brilliant for downloading large files. Like, that's what it's really made for, the transfer of long streams of data. But as you see yourself, we've got 3 megs of data and roughly 108 to 110 connections. That's not long-lived. That's incredibly short-lived and chatty. And in fact, to compound that, we're actually seeing in HTTP 1.1, 74% of our connections just carry a single transaction. That's exactly what we were getting with HTTP 0.9. Request, pull it down, close it. So there's a quote that I really like. It originated in the motor industry with Jackie Stewart. And he's basically saying that you don't have to be an engineer to be a racing driver, but you do have to have mechanical sympathy. So what he's saying here is you don't actually have to understand every single way to put a car together, but you have to understand how the car drives to get the most out of it. So from a computer science perspective, we mostly know this term to do with like Martin Thompson and the work that he does with Disruptor in terms of building high performance trading platforms in Java. And he does that using like a ring buffer, so you don't actually do any garbage collection. And it's absolutely incredible stuff, but he looked at the JVM and he built an application that then worked in harmony with the JVM. We are absolutely not doing that with websites. We are not working with TCP at all. We are trying to work against it. And there's no surprise then that it's kind of highlighted a number of deficiencies in HTTP 1.0 with our current way that we're using it. So there's header blind blocking, lack of parallelism, and protocol overhead. So we're going to step through each of these. And again, this is really what you see will have arisen, or the problems that have come about because of the way that we're building sites. So HTTP is a serialized protocol. So you can only have one request active at any point in time. So if you had a queue of requests, they will be processed sequentially. So as you can see from there, any slow request then will hold up any requests that are following it. And while that mightn't seem like a massive issue to begin with, when you actually look at the effect on bandwidth utilization, it actually becomes quite serious. So in this particular case, we're making a request for index.html. Server thinks about it a little bit, processes it, and serves back that content. Then we make another request for the style sheet, and we get that back. At this point, though, in the request graph, nothing is happening. Like, the line is just dead. So if you looked at like your Google developer tools and you ever looked at how a web page loads, you'll get loads of just like white space in between little bursts of activity. That's latency. That's exactly this network idle time that I've been showing you. So the other major issue that we have is protocol overhead. And these really come about from headers. So HTTP is a stateless protocol. So any state that we need to pass, we actually send it to the server that comes back to us again. And a couple of major problems with this is that on average now we send 800 bytes worth of data back to the server and back again. But this is uncompressed. So we spend a lot of time gzipping the bodies of our resources. These headers and the cookies, they're not compressed at all. Particularly if you consider slow networks, where you might go to your mobile as well, that can have a real serious impact on performance. So where there's a will, there's a way. And we have overcome, or done our best to overcome these, by really cobbling certain best practices together over HTTP 1.0. And the one that we might be most familiar with is domain sharding. And what we're looking to do here is overcome the lack of parallelism in the protocol. So I said before you could have one request and one response. But obviously we want our data faster, we want it quicker. So instead of just limited to the 6 concurrent connections that the browser will create to any host, so as a matter of interest, when HTTP spec was originally created, it was a maximum of 2. But again, as our experiences have demanded that we build richer and richer things, this has now grown to 6. But 6 is not enough. So what we do then is we actually just create separate domains that might go to the exact same host, and then we can have 12 connections or 18 connections. It's brilliant. We could just have as many as we want, and we could put it all down. And in this case, an origin is a triple of the protocol, the host, and the port. So these could absolutely be on the same machine. And you might think that this is an absolutely wonderful outcome. But again, it comes with a cost. And actually, a quite surprisingly high cost when you actually dig into it. So what does it actually take to establish a TCP connection? So every TCP connection starts with the 3-way handshake. We probably all would have heard of it. You send the synchronized packet, you get an acknowledged packet, and then you get the acknowledged packet. That round trip happens before any actual data can be sent. So the round trip time, if you looked at like the speed of light between Perth, where I work, and where we are now, is 20 milliseconds. But we all know, as we've seen before, that we can't actually get our networks to operate as if they were in a vacuum. So in real life, it's actually more like 50 milliseconds. So before we're doing anything, this is 100 milliseconds before I've started even sending any data. But we use HTTPS now, don't we? So again, this is an unoptimized handshake. So I'm actually showing 2 round trips here. Again, this could be 300 milliseconds before any data gets served. There's probably some people in the room now and go, oh, you could use TLS false start there, and I could, remove 1 round trip. You could. But this is just to illustrate again that the cost of even creating a connection before any data is sent is actually quite high. And we're not done yet. So 300 milliseconds has passed, and we're ready to send our first actual bit of data. But how fast is the internet? We don't know. And TCP has certain algorithms that basically prevent us from just firing as much data down the pipe if it's not actually going to reach the server. These are congestion controls, and it's got TCP slow start. So to run you through an example, let's just say I wanted to grab one image, my avatar, which is just 50 kilobytes in size, so tiny, should be happened almost instantly, shouldn't it? But you can only send 10 TCP packets at most on your first connection. That is the biggest initial window size you could have. So that means the server can send at max 14,600 bytes. Where did that number come from? So the maximum transition unit for TCP is 1,500 bytes. And then there's, I've taken off, some header, some sort of like bytes off the top just for IPv4 headers. So we're there with 14,600. That comes back to the server, and I acknowledge each of the packets. So I can add each one of those acknowledgements to the initial window size of 10, and hey presto, I could serve 20 the next time. And finally, the last round trip, I'd send the remaining 6 TCP packets. Still doesn't seem too bad. You get that at roughly, again, 300 milliseconds. But the key point here, if that was an already created connection, if that was a warm connection, that would have been one round trip, because the image would have easily fitted in the maximum TCP window size, even if you don't introduce window scaling. So what you could just see from creating short-term, short-lived connections, you have an upfront cost of actually establishing the connection, but then even before you get the maximum benefit of that connection, it takes a number of round trips as well. And you've already seen 74% of connections only have one resource. So this is happening a hell of a lot. Even worse than this, each one of these 18 TCP connections that we've now created all vie for limited resources. So TCP has very clever congestion control algorithms, but they're not aware of each other. So on your machine, each of these are fighting for that little bit of bandwidth you may have. When it can't get enough, packets will be dropped. And again, you'll be back into the exact same cycles I showed you before. So what I hope we're seeing now is, while we might think there's certain optimizations that we can apply naively, just domain shard all the things, there's actually quite a lot actually going on the back end. So far we've been talking about application level optimization, just things you can do to improve your own page speed. I work at BankWest, and sure many people work in the enterprise as well. And we have a very clever networking team, and they actually apply a quality of service policy over our network. So if you actually have an application that's behaving badly, you may actually be running against not only TCP, but your organization's quality of service policy as well. This app has opened up 18 connections. What's it doing? Absolutely limit it as well. So I guess anybody is working in an enterprise, have a chat with your networking team and see what policies they've applied or may not have applied. So a couple of techniques then that we use to improve performance. So we create image sprites. And the rationale here is, instead of pulling down loads of small resources, we make one big image, and we basically pull down that image, and then we select certain portions of that. And this is actually quite effective. So we actually reduce like a lot of round trip times to the server. But as always, there's trade-offs. So again, in this case, the little icon that looks kind of like something you'd see on a toilet door, if that changed, all of these other images, if you've had it cached on the browser, you'd have to invalidate it and pull it down as well. So there's always trade-offs. So you get poor cache semantics with these. And what we're really dealing with is trying to trade cache efficiency for reduced requests on the network. So you really have to see about the volatility of your resources, see whether these techniques make sense. So on a similar vein, we stick resources together. So head-of-line blocking is costly. And again, we're looking for other ways to reduce the number of requests that go across the network. So again, instead of downloading many small ones, let's stick them together and download a few large ones with the same content. Instead of images this time, though, we're talking about JavaScript and CSS. And we concatenate them, and we minify them, and it's great. Same sort of thing. What happens if just one of those JavaScript files change? The entire bundle is invalidated. So this probably starts you thinking about, well, what should go in a bundle? And you should always try to group the volatility of the resources together. So if you've got your own JavaScript resources that change rapidly, you don't stick it with jQuery or something that doesn't change a lot. You'll just force your users to download that time and time again. So there's actually quite a lot of tuning involved to actually get the most out of techniques like this. We inline resources. We basically stick other resources within other resources. And again, there's perfectly valid use cases for this. So a web performance optimization technique from years and years is to inline your CSS for above the fold content on your page, so it doesn't have to round trip, because browsers will block render on JavaScript and CSS. That's all good. If it's just in the page, it can render it straight away. But we also stick images and other things in data URIs, so actually embed them in pages, embed them in CSS, again to remove these round trip times. There's a lot of pernicious sort of side effects of this as well. If that image appears on multiple pages, all of those pages will have to be invalidated to actually refresh that image. You could be sending more data across the wire as well. all in all, these practices create a tension between what we want to do in dev and what we want to do in production. So while we're in development, we just want to have the JavaScript. We want to be able to debug it. We don't want it minified and uglified and everything else. We just want to be able to use it. So how do we actually handle that? That's extra complexity that we have in our build pipelines, and build tools can help. So we've got, Grunt and Gulp, amongst others. So this is probably the simplest Gulp file you will ever see. We're just grabbing a bunch of JavaScript, we're sticking them all together in a bundle file, we're minifying them, we're creating a name based on the hash of the contents, and we're sticking it in this distribution folder. Anybody who uses this stuff themselves will probably know it's about a quarter or a tenth the size of the ones you will actually have. And the cost of such tooling is additional complexity. Like, we just accept this stuff as being normal. Oh, you have to have your Gulp file. What are you going to do, Rob? But when I started web development, I had two different ways of adding an event handler to see whether I was targeting, IE or, Netscape. Right now, we'd absolutely think that is bonkers. We will start seeing that, all of this sort of like concatenation, that will just become unacceptable in the future. There's certain things with minification. We'll continue to do that. That makes sense. Like, reduce the amount that you send across the server. But all of these other hijinks that we have to, try to coerce resources together, yeah, it's something that needs to change. So fast forward then to 2009, and a number of researchers at Speedy then were saying, okay, well, how can we actually let or allow web developers to remove these sort of band-aids that we've been doing? And I started looking at, well, what would we really want to do if we were to build a new version of HTTP? What features would we look to introduce? And I'm not going to spend too much time on Speedy itself, because this is the precursor for HTTP 2. So many of its features have met more or less one-to-one into HTTP 2. So as we explain HTTP 2, you'll transitively understand what was happening in Speedy. And the first step of this exercise was basically to look at what the performance constraints on web pages were. So for that, they ran a controlled experiment. So they took a number of websites, and first of all, they looked at bandwidth. So they basically said, how does page load time change with regards to bandwidth? So they started with a 1 megabit per second link, and they saw that they got a page load time of over 3 seconds. Then they doubled that speed to 2 megabits. They got an amazing performance improvement. But then they increased it to 3 megabits. Got a little bit of a performance increase, all the way up to 5 megabits. And after that, you're only getting single-digit improvements. So what you can see from there is, in many cases, increasing your bandwidth past 5 megabits per second isn't actually going to improve your browsing experience. So the MBN will improve downloading or streaming video from Netflix. It probably won't actually increase your browsing speed or your browsing experience much at all. Then they looked at latency. And they started ratcheting down latency from 240 milliseconds on the left down to 0 on the right. And what you could actually see is, as latency decreased, you got a linear improvement over time. So what this tells us is, in most sort of like modern contexts in which we use it, where we've got good network, it won't actually be bandwidth that is constraining you. It will be latency. And this is really the foundation of, or the principle which HTTP 2 was designed. So HTTP 2 is about low latency transport of content on the web. That is really the angle at which it came. And adoption is rising fast. So this came out in 2015, and already we have over 16% of the sites worldwide using it. And that's accurate as of yesterday. And that mightn't sound like a large number, but it actually represents over 50% of the traffic on the web. So you could really see the large sites like Facebook, like the others as well, they have adopted it as well. And HTTP 2 respects all the existing HTTP semantics. So headers, cookies, all of that, that hasn't changed. And let's face it, it's probably a good design choice. Breaking the web wouldn't have been a good idea. So one of the really major changes with HTTP 2 is how data gets transferred across the wire. So instead of all these separate connections, Everything goes over one single TCP connection per origin. But you're probably thinking, well, didn't you just say that we got really bad bandwidth utilization on a TCP connection? Wouldn't that make the performance absolutely horrible? And this is where the binary framing layer comes in. So unlike its predecessors, HTTP2 is a binary protocol. No more telnetting, people. You can't do it anymore. But what we actually do is take the request as it would look like in HTTP 1.0, and we actually frame it into sections of data called frames. And then what we can do with them is, again, in this particular case, we have headers, and they will map into a headers frame. We got data, and data will map into one or more data frames. And there's actually 9 different types of frames as defined in the spec. And some of them are pretty much the same functionality as we would have already expected, but there's some other new features that allow us to do some pretty cool work, which we'll explore in a little bit. So once we have a request, and we've mapped that request to a number of frames, they form part of a stream. And now across the wire, we can actually multiplex these streams. So it's no longer one request, one response, but we can actually just send multiple streams across the wire. And it's actually bidirectional. So in this case, we've got a little bit of stream 1, a bit of stream 2, a bit more of stream 1 and 2. So that's actually how they've got efficiency on the wire. So no more head-of-line blocking at the application level, because we can actually multiplex all of these streams back and forth. So again, from a diagram perspective, this is actually great, because instead of this sort of cat and mouse game that browsers need to play today with HTTP 1.0, where they're saying, I'm parsing a web page. I know I have 6 connections that I can send to the server. As I parse the DOM and I find, another resource, should I ask for that now? What happens if I get a CSS or a style sheet that's coming up that really should have higher priority? Should I hold on to a request? Do they play all of these guessing games? We don't need to do that now. Basically, as the browser or the client comes along with a request, it just sends it to the server, because it knows that it can then have that request or that stream prioritized. So we can apply a quality of service over it. So remember, with HTTP 1.0, we had 74% of connections carried a single transaction. With HTTP 2 and the binary framing layer, that plummets right the way down to 25%. So we can see we're actually getting a lot more value out of the underlying TCP connection. And there's plus sides to this as well. So now that we can actually say we don't need to glue all of our resources together simply to reduce the number of round trips, we're actually finally in a position where we can get value out of HTTP caching, or as much value as we really should have been with this. So again, I hinted at it a couple of slides back. You say, well, with HTTP 1.0, we had to carefully massage the requests that we sent to the server. But now we can just send them straight to the server. And this really comes down to now having to invert this relationship whereby the browser was responsible for prioritization. Now it's the server. And how does it actually do that? So with stream prioritization, each of the streams themselves can have a number of factors that define this priority. So it can have a weight. And a weight basically defines a number between 1 and 256, which hints to the server how important is this resource. So for instance, you might say an image might have a priority of 5, but then you say this CSS is really important. I want to give this a priority of 10. And I guess the key thing from there is that these are really just hints that you send to the server. The server is not obligated to respect them. It generally will, but it has certain heuristics itself as well. What you can also do is you can set up dependencies between streams. So in this particular case, we're saying that once stream A has been delivered, equally divide the available bandwidth between streams B and C. And you could see that there's going to be equally distributed because the weights are the same. And it's a simple algorithm like that, simply dependency and weight. But it allows us to do some really clever prioritization of workloads. So We can also dynamically change the priority of a stream. And listen to this for a scenario. So again, the user loads a page, and there's an image in the top left-hand corner. And you say, OK, well, absolutely, this might be quite a big image, but it's really important to the user at that point in time. But then we scroll down. That image goes off the screen. Before, we would have had no way of telling the server to stop sending that. We would have still got all the data back down to the client. Now we can just change the priority of that stream and go, I don't really need that image anymore. You could hold on to it. And then we will reprioritize the available bandwidth to other resources as well. So I guess the key thing from here, this isn't a static graph that gets created at the start of page load. This can change based on context throughout the page load time, render time, and runtime. HTTP2 effectively means HTTPS. Okay, the spec itself doesn't mandate that you use SSL for your connections, but in practice, you had to. And there's a lot of plus sides to using secure connections. We obviously, as users on the web, we get our data encrypted and our privacy respected. But this actually wasn't the major driver for going down HTTPS. And it's a bit surprising, but the internet is absolutely riddled with middle box debris. There are NAT devices, proxies, IDSs, WAN optimizers that all look at traffic over port 80. And they try to do their best to improve things. So they will look at it and say, OK, well, I'm expecting HTTP 1.0 shaped traffic that comes across. Let me see if I can compress it. As we just learned, though, HTTP 2 traffic is binary. They don't understand this. So in the face of this, they either do one or two things. They either just fall over, or they think it's nefarious or dodgy, and they will close the connection. And initially, when they went to roll out Speedy, they did some tests in this area, and they saw that between 20 and 30% of traffic fell to this exact problem. And again, if you're building a new protocol, 30% of traffic failure on the web would absolutely have not been acceptable. Swapping it over to HTTPS, everything worked smoothly. So while the HTTP2 spec doesn't mandate that you have to use HTTPS, it does have some caveats to say if you do, you have to do it to a certain level of standards. So you have to use at least TLS 1.2. Most of us would be as well. If you had like the SSL Heartbleed issue from last year as well, you'd probably be aware of that. And it also has an opinion about cipher suites. So it recommends that cipher suites with perfect forward secrecy are used. So by that, it's effectively in some of the old RSA-based cipher suites, they reuse the key for negotiating the connection between the server and the client to actually encrypt the traffic as well. So if you've got your hands on that key, you could actually use that to decrypt all the past traffic that had gone between that client and server as well. Really scary proposition. So with perfect forward secrecy, you can't do that. So even if you compromise the key for a particular session, it will not allow the attacker to decrypt old traffic as well. So the spec defines quite a long blacklist of cipher suites that you should not negotiate over HTTP2. And if you're interested, you can check it out in the spec. And this has actually had some really positive impact on the web as well. So HTTPS adoption has more than doubled in 2016, and now accounts for more than 50% of traffic on the web. So I think even irrespective of HTTP2, this is a really good outcome. But for many people deploying HTTP2, HTTPS will actually be the biggest issue, particularly if you host third-party content and you've got mixed authorization or authentication on. That's all a bit nasty. There's actually a really good blog post by Nick Craver, one of the engineers of Stack Overflow. It's really like a book. And he basically details all of the challenges that Stack Overflow faced when shifting to HTTPS over like a 2 to 3 year period. And it's an absolutely amazing read. So if you have some time, absolutely encourage you to take a look at that. So HTTPS also gives us some benefits in terms of how to actually negotiate a HTTP2 connection. So they've created this ALPN, so application level protocol negotiation, that as part of the TLS handshake allows you to negotiate what protocol to use without doing another round trip. And it's quite simple. As part of the client hello, the client basically lists what available protocols it understands. So if it understands HTTP2, it will say, okay, that's cool. I will put HC in the list. The server will then take a look at this and say, what protocols can I talk? And then respond back to the server. So this performs the exact same role as NPN did in Speedy, except with Speedy, it was actually the client that ultimately chose what protocol to use. So when it has actually got ratified into a standard, they switch that responsibility to the server to align with other protocol negotiation standards that exist on the web. So we looked at before that protocol overhead was a really big problem with HTTP 1.0, all of that uncompressed header data. So as part of the spec was actually a separate RFC. They created HPAC. And what this does is it comes in two parts. So first of all, we have a static dictionary that is defined in the specification. And what this does is it maps common values. So for instance here, the accept header to numeric values within this dictionary. So what this lets us do, instead of sending accept or a user agent header, let's just say across the wire, we would just send the number 19. That's it. So it's a really simple translation, but incredibly powerful. And in fact, if that header hasn't actually changed between this communication, it won't send it at all. So we can radically reduce the amount of data sent back and forth between the servers. So there's a static dictionary for all the predefined standards like user agent authorization, often common values for status headers as well, like OKs and no contents, not modifieds. But there's also a dynamic dictionary as well. And this is for maybe headers or values that you've created yourself as part of the application. And they will also go through the same process of being Huffman encoded to a numeric value, and then that key just being passed back and forth. So domain sharding, we said before that we can span connections across multiple hosts, and some pluses, lots of minuses. And actually HTTP2 has a trick up its sleeve for this. So it will actually coalesce two connections if a number of criteria are met. So if you have two separate origins that actually map to the same IP address and are covered by a TLS certificate that covers both domains. So for this particular case, we can see that the CND subdomain of example and example.com will have the same, we'll have an SSL certificate that covers both. So we'll actually coalesce that connection to just have one between the client and the server. So this is a good technique, again, if you have a current site that you've got to have some users that will negotiate HTTP 1.x and some will negotiate HTTP 2. You can actually start architecting on the back end to actually optimize for both scenarios. So I've been talking a lot about latency. And maybe there's a few people in the room here that says, oh, I wish they had just sorted out cookies. So latency was really the biggest issue that the working group saw. It doesn't mean that HTTP2 will stop here. And they will continue to iron out some of the other issues. It's just that latency was the biggest one they wanted to get fixed up front. And probably the key thing here is, this is from the head of the working group. And it's not magic. You're not just going to stick it onto your site and it go 50% faster. Probably a lot of the hacks that I mentioned before are actually now counterproductive. So we actually have to start reversing a lot of that to actually get the major benefits of HTTP2. And I guess the key thing from there is take a scientific approach. Don't assume, make a change, and measure it. And there's some tooling that can really help you with it, which we'll discuss later. So one of the key features of HTTP2 is server push. And this really changes the way that clients and servers interact. So what we can see here is an example where the client asks for index.html. And including it gets back to HTML, but the server says, oh, if you ask for the index.html document, chances are you will want the CSS and the JavaScript as well. Here you go. And that's absolutely fantastic because we actually save ourselves another request or another round trip from the server. And of course, the client can actually choose then to reject that push by just calling a reset stream. So this is a similar technique to what we might have done if we were looking to deprioritize or just cancel a request from the server. We can say, I don't want this stream anymore. And this actually opens up a huge amount of potential benefits for smarter servers. So you could build a web server that then, and Jetty has an implementation in the Java space already, that will actually look at how users are actually interacting with the website, and actually, based on the referrer header, build up user trending of traffic, and then actually optimize itself about what resources to push. So there's a whole level of optimizations that just weren't possible before. This is really, as an industry, what we do. So if anyone's familiar with the JVM, it's got Hotspot, which will effectively look at a piece of code that's operating slowly, and then either look to inline a method or improve it as well. This is the same sort of runtime performance improvement that we would have in that space, just applied to a different context. And if you have certain devices, let's just say that you're on an emerging market or on your mobile phone, and you really say, actually, I'm happy to just live with the latency of maybe that extra sort of round trip. I don't just want the server to speculatively push data to me. In the initial connection negotiation, you can just define in the settings frame, I don't want to be involved with server push. And it's as easy as that. A key thing to understand about server push is it's actually a really low-level networking feature. And in fact, anything that's not exclusive to browsers can actually leverage that. So from a kind of like a page flow perspective, I've actually, just for the interest of brevity, I've actually excluded two caches here, the preload cache and the image cache. But when a page actually looks to resolve a resource, it will actually go through a number of hops. So first of all, it will look at the service worker. Do I have a cached copy of that resource at the service worker level? If it doesn't, it will go to the HTTP cache. If it doesn't exist there, it will then fall back to your push cache. And the push cache itself lives in the HTTP2 connection. It is tied, it is part of that connection. And there's a couple of things we can have from that. So you can actually push things that are marked as being no cache and no store. It doesn't respect HTTP cache headers, which is cool. It's absolutely what you'd expect. But you can only read something from the push cache once. That might sound like a bit of a limitation, but effectively, in many cases, it will just move from there to your HTTP cache anyway. But there's a couple of things to be aware of. If the connection is closed, your push cache is gone. So from there, don't push things that you think the client may need at some future point in time. Push things that they will need almost immediately. And more gotchas. So if you have any authentication on your site, authenticated requests and unauthenticated requests will actually go down different connections to the server. And you really need to handle these appropriately, or any unauthenticated requests won't hit your push cache. And this mainly means for if you're doing a fetch, including the credentials. There may be certain cases where this won't work, and if that's the scenario, you'll have to go into the service worker and actually change how that network call is made. And browser support for server push, it's a little inconsistent right now. Like the binary framing layer is absolutely rock solid, but there are certain edge cases with server push that you could really see that you won't be getting the most value from it. So Chrome, very good. Firefox, very good. Safari, shocking. Edge, kind of okay, but really from today's scenario, I would really only want to push to users using Chrome and Firefox. So from their user agent sniffing to just determine what user agent the client is using, and based on that, push or don't push. This is just because it's an emerging technology. Like hopefully if someone's watching this video, in a year's time, they could probably ignore all the advice that I'm giving for this 30-second period. So a key thing is if you get server push wrong, it will actually hurt performance. So if you're pushing resources that the client doesn't need or the client can't understand or use, then it will be worse than not supporting it at all. So really measure and test this. So if you are pushing content, actually make sure that that is actually being used on the client side. So an interesting observation is, again, the best performance you can get out of a network-based system is actually by not using the network. It might sound a bit counterintuitive, but don't send data you don't need to send. And right now, we have no way of the client actually being able to say to the server, I already have this. Like, don't send it to me again. I don't want it. And there's a new standard that's going to be coming out called Cache Digest. And that will allow the client to basically say, here are all the resources I already have. Here you go, server. If you wanted to push these to me, I'm good. So that's not available as yet, but I really see this as a key feature that will actually allow us to have more value or more adoption of server push. So right now we have a number of ways that the client can already proactively pull down or ask for content to be served from the server. So this is preload and prefetch. So preload will effectively force the browser to make a request to the server to pull down a particular resource. So you might do that if you have a multi-page form. You might pull down on page 1 some content that's needed for page 2. So it's available when the user wants to actually navigate to next. Prefetch is the same, but it's really just a hint. It doesn't force the browser to make that request. So an efficient server push will always be faster than either of these two techniques. But again, given where we are with server push support, I'd actually say these should be your staple bread and butter for today, and then look at server push, mainly when Cache Digest comes along. So what are some sort of like perennial good ideas to be doing with web performance, irrespective of the version of HTTP? So minimize DNS lookups. So that's where you get the domain name, and it has to be resolved to an IP address. That can be quite a costly process at certain times, so minimize them. So requests are actually blocked when you're resolving the name. That's a key takeaway. Reuse existing TCP connections. Bit of a no-brainer with HTTP2. You just got one per origin. But pay attention to credentialed and non-credentialed requests. Creating a connection is expensive. So minimize the number of HTTP redirects. So again, they will either be 301s or 302s, possibly 307s that you throw back to the clients that will then have to follow another link. That's just more round trips. Try to either handle that on the server, but minimize them to the client. So again, minimize the amount of data that you send on the wire. So if there's any resources that you just actually don't need to send, just clean them up. Other than that, effectively set your cache headers. So be aggressive with them. So again, you could actually use, never expiring cache headers if you send, like a hash to the file name as well. There's certain techniques that you can do from there as well. So use a CDN. So CDNs are at their best when they're actually geographically caching data close to your users. But there's other uses for them as well. You can actually do uncached origin fetches. So even for content that's personalized, it can't actually be cached, in an intermediary proxy. What you can actually do is the CDN, you can actually talk to the CDN and you will have your handshake terminated with a very quick handshake. The CDN can actually keep alive a warm set of connections down to the backend servers as well. So you get all the benefit of an already warm TCP connection on the backend. So again, some sort of like unobvious but quite powerful techniques. So hopefully at this stage, you've said HTTP2 can really solve some of the problems that I have. So here's a couple of tools that will actually help make your life a little bit better. So Chrome internals, absolutely fantastic. It will let you browse all of the HTTP2 traffic and actually see frame by frame what's sending across the wire. So this should be your bread and butter on a day-to-day basis. From a performance perspective, web page test is absolutely fantastic. That will actually let you do a number of tests from geographic locations around the world to your site to actually test across different network conditions as well. Really powerful. Fiddler is out because C# doesn't support Alpin yet, but you can use Wireshark. There is a bit of a gotcha with Wireshark as well, insofar as you actually have to export the SSL keylog file to actually allow Wireshark to decrypt that traffic. And that's actually due to, again, the perfect forward secrecy. So there's an environment variable that you can set that then Chrome will actually export that keylog, and you can import that into the Wireshark settings then, and it will be able to decrypt that session traffic. So again, loads of blog posts online if you want to take a look at that. So far we've been talking about HTTP2 quite a bit. So what's going to be coming next from a protocol perspective? So serving HTTP2 over TCP, we've solved head-of-line blocking at the application level. That's absolutely fantastic. But we still have head-of-line blocking at the TCP connection level. So a single drop TCP packet can introduce head-of-line blocking for every single stream. That's obviously not so great. So researchers are currently looking at Quick. And from here, that's going to be based on UDP, which you generally use for jaggy or sort of like latency sensitive media. But what this will do is it will actually improve the multiplexing of streams such that if a particular packet or datagram is dropped for one of those streams, only that stream itself will be affected, not all the streams. And again, another key goal of Quick is to reduce the cost of initiating a handshake between the client and the server. So this will actually allow for a 0 round trip resume if you're actually resuming a TLS session, or 1 round trip for a new session. And in fact, some of these features are actually already making their way into TLS 1.3. And in fact, another really good benefit of basing on top of UDP is they can actually iterate incredibly quickly. So TCP is actually built into all the kernels of all the operating systems that we have. So its advancement is glacial. With UDP, they can quickly iterate on that. So actually what you'll see over time is the features that we've actually proved off the right-hand side in UDP will actually then start making their way into the TCP stack. So congratulations, you now know HTTP2. So seriously, continue to learn with it. I think it's going to be a really powerful technology. And in fact, it's really the biggest change that's happened in 18 years in the web. So I strongly encourage everyone to take a look at it and do something awesome with it. Thank you. We have 4 minutes for questions.
What's client support like for HTTP2, and are you going to make things worse for HTTP1 clients than if you start unbundling all your sprites and everything?
So the question is, if you optimize for HTTP2, would you actually be disimproving the experience for HTTP1 clients if you start unbundling the resources? So the short answer for that is yes. But what you need to do for your site is profile it. See how many users are using HTTP1, how many are trying to negotiate HTTP2, and then you will decide on a tipping point. And then when it actually makes sense to start migrating across, do it at that point in time. I guess other features as well, that if you're going to say, okay, well, where does the industry go as a trend? Maybe you just start building in new stuff from a HTTP2 perspective, and maybe you're absolutely fine with having a little bit of impact to your HTTP 1.1 users. I guess the other thing as well, HTTP2 will most affect users on a high latency network. So again, also look at the connection teams. So if you use like real user monitoring and another sort of like traffic profiling technique like that, you can then actually say, okay, well, if we have users negotiating HTTP 1.1 on a high latency connection, just swap them over right now. They will get far more benefit out of moving to HTTP2 for those scenarios than the micro optimizations you get with bundling. So generally you will see between about a 20 and a 30% speed boost from going to HTTP2 without doing a thing. And that's from the studies that they've done on both Speedy and HTTP2 since it came in. Obviously, if you have a site that is heavily sharded, you mightn't see that level of benefit, initially, but you could start either like re-architecting your backend to either have multiple shards actually point to the same host and actually then be able to support the best of both worlds for HTTP1 and HTTP2 clients. But yeah, it's really a measure and learn and take small steps from there. So I guess like the key thing from there is instrument. Like you have to have instrumentation for everything. Like don't make decisions for migrating across to HTTP2 based on gut feel. Like measure it, and when you feel it's actually going to benefit your users, migrate across. They won't thank you if you make things slow in the short term. I think we have time for one more question.
So do you see any of the use cases for WebSockets being taken up by this?
Really good question. So do we see that WebSockets will be replaced by certain features like your server push? In fact, the WebSocket community had many of the similar findings to what we had with HTTP2 as well. So they initially tried to put WebSocket traffic over port 80 and found that the middle boxes absolutely, caught them with the same issues from there. I actually see them as complementary technologies. I think for bidirectional flows, WebSockets still make a huge amount of sense. I think server push again it's a bit too early to say whether it will reach like broad appeal like beyond the sort of like client server web page sort of architecture. But no, I definitely don't see them as that a WebSocket's going away anytime soon. I think that's it for time. But if anyone would like to have a chat later, feel free to come up. Cheers. Thank you.